Yes, we are recording. Okay, sorry. If you're watching this, future students, I'm not talking to you guys in the room. If you're watching this right now, you totally missed simultaneity and an introduction to special relativity. I didn't record it because I'm a dum-dum. But we are now starting time dilation, which should be very interesting. So just a quick recap. We did recently establish that what events appear simultaneous to one frame of reference are not always simultaneous to another frame of reference. And questions should come up about how that is possible. The important thing to remember with special relativity is always the laws of physics are upheld in a non-inertial reference frame, including the speed of light. The speed of light is c in a vacuum in any inertial reference frame. Sorry, I said non-inertial before. Inertial reference frame, okay? If you remember that simple fact, all of these rules, all of these things, all of these results all fall out of that fact. In an inertial reference frame, the laws of physics, including the speed of light, are upheld, okay? If you just know that, then all of these things can actually be derived through very, very complex thought experiments, as was the case when we developed the idea of time dilation. Commonly referred to as a moving clock runs slow. Now that's a fairly apt little simple way of remembering it, but we'll explore why it can also be a bit misleading in a moment. Let's start with just the formula. And this is a formula directly from your formula and data book. So let me just check the notation from your formula and data book. So there it is there in your formula and data book. That is our formula for time dilation, okay? So get used to seeing that. There are two T's there. First T is relative time. T0 is proper time. And we're going to spend a bit of time wrapping our head, wrapping our head around those. But let's quickly get that formula down in our books. So it is T equals T0 divided by Okay, any questions about the shape of that formula, about what's going on there, or is it clear? T0 divided by, all in brackets, the square root of 1 minus v squared over c squared, okay? Now let's just define those terms as well to make sure that's clear. So I'll shift that over ever so slightly, and we'll establish that where T equals relativistic time, or relative time. T0 equals proper time. Now, straight away, I want you to get out of your heads that that one's correct and relative time is wrong. Again, they are each correct for their respective observers. It's just a way of appreciating which observer is which. V, of course, is the relative velocities. Helps if I can spell relative. And I'll remind you that when we talk about relative velocities, we need to make sure that the velocities we're discussing are actually relativistic. That is to say, they are fast enough that relativistic effects come into play, okay? Otherwise, just use Newton's laws. They work perfectly. If we're moving slowly, Newton's laws are fine. And of course, c is the speed of light, in case I need to tell you that. And units are all SI, standard units, meters per second, seconds for time. You will have to work in SI units for this formula to work. So if you're doing something in minutes or hours, make sure you convert first, okay? All right, most people seem to be done writing, so let's just quickly discuss this. I want to make a couple of quick points. First point is this formula can, of course, be arranged. Common thing is just to multiply that over to there to solve for proper time rather than relative time. So you can do it both ways. And speaking of that, let's be very clear about this. We're going to get some notes on proper time. We're going to look at some examples because it can be a bit confusing. But the very simple way of remembering this is remembering this fact, okay? When we talk about these, it's always relative, right? So there are two frames of reference at minimum involved in these questions, okay? If you are locked in a capsule with no indication that you're moving, no windows, no nothing, it's just you, and you're moving at a constant velocity, you're not accelerating, you have no way of knowing your velocity, you have no way of knowing how time is changing for you, nothing. You cannot measure any change to the universe. Everything is as it should be as far as you're concerned. Even if you're zipping along at the speed of light, you would not notice anything different. You'd look at your stopwatch, it'd tick along 1 second, 2 seconds, it'd feel like a second, your heartbeat would be about typical, all those sorts of things would be normal. But if you get a window and you look outside at another person floating along in a similar situation in their capsule in the middle of space, whatever, and they're moving relative to you, there's two observations you can make. You can make an observation of yourself and your frame. You can make an observation of a frame that is moving relative to you. Now, to make the observation of the frame moving relative to you, you have to look out your window at their ship. Now, when we're talking about time dilation, what we're often talking about is looking at their clock. That's the way I want you to think about it. So rather than a window, they have a big clock on their ship, which is counting time with them. But they're moving relative to you. Now, this is where this simple statement works. We see that clock as moving. So that clock runs slow. We watch that clock and we watch ours. 1 second, 2 seconds, 1 second, 3 seconds, 4 seconds, 2 seconds, 5 seconds, 6 seconds, 3 seconds. We watch our clock and it seems normal. We watch their clock and it's like they're in slow motion. And physically, if we watch them, if we recorded data from that ship as it was moving, every year we looked at a photo of them, they would age slower. Everything would happen slower. Their motion would appear in slow motion. Any gravitational forces around them would act slower. Everything we saw from that ship as it moves at a relativistic speed would be observed to happen slower. While we're in our ship and everything is happening normal. Here's where it gets crazy. If we shift frame of references to that ship, everything is mirrored. They see you going slower. To them, everything is normal. They're watching their clock going 1 second, 2 seconds, 3 seconds, 1 second, 4 seconds. Everything that they see you doing. So you're sitting in your ship going, oh, they're running slow. And you're sitting in that ship going, oh, they're running slow. And it happens both ways. And that tends to feel really contradictory. But it does work and it does happen, okay? So let's take the International Space Station as an example, right? We have said a couple of times that time's running slow for them. They have to adjust their clocks all the time. But guess what? They look at our clocks, we're the ones running slow. They just say, let's adjust our clocks to match them. But we could be adjusting to match them just as easily. It could be our clocks that are wrong. Their clocks are measuring time perfectly fine up there. It's just different to ours. Yep. Yep. So to us, they are running slow, so they would need to go forwards. No, so we measure our time and we get them to adjust their clocks to match them. So, yeah, we'd have to put our clocks forward to match them. So we just decided we're the better ones, let's use our time. No, they bring their clocks forward. She's asking a good question. Because when you, so there's a breakdown here where we actually break inertial reference frames. There is a communication between us, and when we communicate between the ships, we're actually changing, that information is changing an inertial frame. So we break the idea of an inertial frame. So this only works if everyone continues in their inertial frame. So as soon as that space station adjusts their clocks, so we send a measurement. We say it's been 6 seconds for us. When they get their measurement, they'll have had, we're going to do examples on this in a second, but they'll have had a different amount of time. Let me get this right because this can mess you up. When they get our 6 seconds, for them, it will not have been 6 seconds. Yes, it goes both ways. But the reason it ends up canceling out in the end and everyone ends up back at the same time is because for them to then come back to us or for them to then send their time to us, they break their inertial frame of reference. They have to accelerate, essentially. Their information leaves that inertial frame of reference. And that's when things are different. We'll look at paradox. Yeah, no, what you're asking is called a paradox. And these are the exact sort of paradoxes we're going to work towards in a couple of weeks. And you guys are going to be thinking about these paradoxes that seem to break the rules. And we'll find out why they don't actually break the rules and it still works, okay? For now, let's talk about very specifically proper time because we need to establish this language. Now, this is arbitrary choice. Who we choose to be the proper time is arbitrary. But scientists have agreed that proper time is the measure of we'll leave it there for now. I have one more example which we can discuss, but I'll just leave those ones for you guys to get down. I want you to discuss with the person next to you or in a group of 3 or whatever, who experiences proper time in each of these examples? Is it the person on the train, the scientist on Earth? Who is experiencing proper time? And the way we like to define it is the time that can be measured by one clock present in both locations or places of event. Okay? So for the train, the places of event are point X and point Y very clearly. Right? So who could hold on to one clock and that clock would be present at both events, point X and point Y? There in the places. Have that discussion amongst yourselves. Do it for question 1 and 2, example 1 and 2, and we will discuss in 4 minutes. So the answer to that first example is going to be an observer on the train. Because if you imagine them as holding their clock comes with them from point X to point Y. They make the measurement without changing their frame of reference, and the measurements they make are at the same location as the events whose time is being measured. It is tricky, but that's the way of defining it. Now, question 2. Hands up those of you who think it's the astronaut measuring proper time. Hands up if you disagree. Gentlemen, do you want to explain why you think it's an observer on Earth that experiences proper time here?
Well, I'm thinking of the event is...
Anyone got an argument against that? So what's the event being measured? So the light being turned on, and then we could say turned off again after some time. I did actually write that in the original and I thought I'd simplify it, but yeah, light turned on and then turned off perhaps. Yep, that's the event that we're measuring the time of. Who's stationary to that event? Who is in the frame of reference where that event can be measured at the same place? Scientist. See how that is really counterintuitive? Because in the first one, you go, oh, so it's just the one that's moving. Who's moving? Who is moving there?
Flying past.
Yeah, but so is the Earth.
Yeah, but it never specified that the Earth is...
It doesn't have to. That's relative velocity. That's the whole thing. But there's no absolute velocity. So no one is still by any measure. Relative to the Earth, they are. Relative to an asteroid floating above, they could be going the exact same speed. That's the challenge, Campbell. That's the challenge. And that's how it works. You are welcome to disagree. You are wrong, but you are welcome to disagree. All right, example 3 is a really tricky one. So let's think about this one together. Using the concept of proper and relative time, and hopefully now we've established that moving clocks run slow. Okay, so when we observe something that is moving relative to us, we observe it to experience time slower. Explain why the muon decay problem came up. We knew that muons only stay alive for 2.2 microseconds before they will decay usually into energy. decay. They can decay into neutrinos, which we'll learn about in standard model, but usually just into energy. Yep. Sorry? We discussed it, but we didn't do it with the frame of mind of proper time and relative time. So I now want you to apply this concept to understand why that experiment works the way it does. It's a particle, it's a fundamental particle, which we haven't learnt about yet. We'll cover it in the standard model. I actually have not looked at this in a while, and off the top of my head, I can't really remember. I think it's a heavy electron, a really big fat electron. What? No, it is a particle of itself. It is just a very rare, uncommon particle. It is a type of electron that is a lot heavier, and because of its shape and size, it doesn't exist for very long. It decays. Yes, but they are a particle of themselves. A subatomic particle is a particle. It's not part of a particle. Muons can pop up in atoms, but they're not stable. They're not generally part of atoms. They can appear, but they will decay. Yeah. Okay, discuss that. Try and give me an explanation. I'll get volunteers to read out what they write. Thank you, everyone. Active listening in 5. Nice and quiet in 4. Looking this way in 3, 2, 1. So, who would like to try to explain, using the concept of proper time and relative time, why we see muons reach the surface of the Earth rather than decaying in 2.2 microseconds in the upper atmosphere when they first are made by cosmic rays bashing the atmosphere? Why does this occur? Alex? Say again? Mm-hmm. So we are watching them moving fast. So we see them, and the time we measure that they're experiencing is the relative time. And is relative time slower than proper time? Is that what you're saying? Yep, you can confidently say yes, because... Yep, cool. Okay. Anyone want to put that in a different way? Say that in different words? Explain that in any more depth? Come on. Alex breezed over that pretty over the top. Anyone want to be a bit more detailed about that explanation? No, that's okay. We'll hear from other people. Have a go. Have a go at formulating this into words, because you will have to. Come on, challenge yourself. Go for it, Kobe. He hates silence. So 2.2 microseconds is relative to... Right. So the muon, when it's moving or when it's at rest in the lab, what are we talking about? Okay, so either way, the muon's time, that 2.2 microseconds, is a proper time. And that's what the muon experiences. Right. Sure, yeah. Relative time dilation. So when we're in the lab with these muons, we're in their frame of reference. We get to measure their proper time. So that 2.2 seconds is the proper time that the muons experience. That's what we measure when we're with them in their frame of reference. But when we actually observe them being created in the upper atmosphere and blasting down to Earth, we see them moving at incredibly high speeds relative to us. They are experiencing their proper time, which for them is 2.2 seconds. We are experiencing dilated time when we watch them. We see that their clocks are running slower. 2.2 seconds has not passed from us watching them. Okay? Now, This brings up a contradiction, and this is what Hannah was touching on a little bit before when she asked me about the scientists on the International Space Station. How is it then that the muon experiences only 2.2 seconds traveling that distance? How does it make it to Earth if we see it traveling this distance so quickly and we see time running slow for it? How is it that it can still experience its time and reach the Earth if it's still only traveling the speed of light? Right, so it would see the Earth as running slower. Yeah? Now this does still bring up that doesn't solve the paradox that Hannah was sort of touching on before. That doesn't solve this concern of how can we both see each other moving slower. There's one other solution here. You haven't learned about it yet, so I've mentioned it. How can a muon travel an incredible distance without moving any faster in less time? For it. How can it seem, from its perspective, to travel a great distance at the same speed as us? Spirals? That would mean it would be traveling the longer distance. We both see it travel the same distance, right? The distance it thinks it's gone and the distance we think it's gone is the same, right? Wrong. This is time-space. This is space-time. They are inseparable. If time can dilate, what else can happen? The muon only experiences 2.2 seconds. How can it cross that vast distance? It's not a vast distance. Space has contracted for it. It can cross that far in 2.2 microseconds because it's a much shorter distance for the muon. That's the only conclusion that works. If two runners race the same distance, one of them gets there in a longer amount of, if two runners race at the same speed and one of them reaches the finish line later than the other one of them must have run a shorter race. Has to be the case. So if we talk about light having a set speed of light, but we can observe it move slower, how can that happen? It travels less distance. We're going to get into that in a second. Let's do an example without all the woo-ha of time dilation, just very simply a train example, a very fast train traveling at 0.8 C goes through a station. If you guys are copying this down, I'm happy for you to notate your title, your example. That way you can always refer to it in your textbook. And then just copy your key information down. What notation do we need to capture this here? What notation do we use for that? Recalling our formula. What is our notation for that? So we've got T equals T0 equals C equals V equals. What do we know? What don't we know? We know what? We know one of the times. Let's establish if it's proper or if it's relative time. Where's our time? Here, 1 second. A woman on board the train measures the time interval from one end to the other as 1 second. Is she measuring proper time? Has she got one clock present at both the starting and ending event? Yes, she measures proper time as 1.0 seconds. Very fast train. Do we know relative time? No, not yet. We'll find it. Big question mark. Do we know the speed of light? Yes, of course we do. 3.00 by 10 to the power of 8 meters per second. Noting that that's in a vacuum, it doesn't matter that the question isn't in a vacuum. It's irrelevant. The formula specifically references C, the speed of light in a vacuum. We don't need to change our speed of light. And V, do we know V? Right, what is V? Is that a useful way of calculating v, velocity? It absolutely is. In particular, because in this example, we divide them. They get divided. So the c will cancel out. We'll see that in a moment. Okay, let's formulate our problem. So t equals t0. Write this formula really big. Really space this out, guys. Organize this nice and neat. Getting this formula clear and communicating it well is a skill in and of itself, okay? Space it out, use a few lines. Don't be scared to fill a book while you start out on this, all right? T0 over in brackets, or the square root of in brackets. Much of a muchness really, but 1 minus v squared over c squared. People who have slightly weaker math when it comes to, in particular, fractions and stuff like that, this can get really messy and confusing. Please stop me at any point to clarify what I'm doing on this board if it's unclear. Sorry about that. That's for you later when you watch that back. All right. We can fill it out. We know that t0 is 1, so this whole thing is just 1 over the square root of 1 minus v squared is 0.8 c squared. Let's chuck brackets around that 0.8 c so that we know the squared is applied to 0.8 c. Yeah? Let's make sure that's nice and clear. Now you're going to see very quickly that this formula will consistently simplify in a really easy way. Consistently. So be ready to see that. You will see. You'll see. You get it? You'll see? Yeah. Okay, good. Thanks for the support. This here, 0.8 c squared. Remember what squared means. I know you're year 12, but people still make this mistake. This means that whole thing is multiplied by itself. 0.8 times by c times by 0.8 times by c. Okay? If you need to, write the step out. Do not be ashamed to just write out the whole step every time. I'm going to shift things around slightly here so I can fit in a bit easier. Squeeze things in. 1 over square root. This becomes 1 minus, what's 0.8 times 0.8? 0.64 c squared over c squared. They cancel. Consistently, the c's will cancel. 0.8 times by 0.8. So distributive law for squares is it applies to both. 0.8 squared and c squared. All good so far? With me so far on this math? Any questions? Can everyone see each step that I've done so far? Okay. Now it becomes really quite a simple, who'd have thought, you know, time dilation from special relativity, Einsteinian math, actually becomes pretty straightforward. 1 divided by square root of 1 minus 0.64. What do we get? 1 minus 0.64, we're going to get 0.36. So 0.36, we want the square root of 0.36. Square root of that is that right? Yeah. 0.6. 1 divided by 0. Did that just become 0.61? Is that about right? Is that what you guys got? Yeah. 1 and I guess that's 2/3. We could probably write that as 5/3 if we wanted. 1 and 2/3, 5/3. Or just 1.67 would be accepted. 1.67. 1.67 what? Look at the difference. How much did the person on the train experience? How much does relative time experience? Now that's at 0.8 times the speed of light. Obviously, this situation is completely impossible in today's day and age. Theoretically, there is no reason we can't travel close to the speed of light as humans. We talk about length contraction and time dilation, but again, for you in your frame of reference, nothing gets weird. Everything is fine. The world around you would look strange, but for the world around you, they're fine as well. So it's not like if you travel at the speed of light, you'll be compressed into a squashed little spaghetti man. It works. You could theoretically do it and be fine. If you accelerate very quickly to that speed, yeah. But if you did it slowly, yeah. There was a spacecraft. I want to say Cassini, but I could be wrong. There was a spacecraft that ran off solar power, and it had a thruster of some sort. I don't remember if it was ion or it was just an electric thruster, basically. And it was very, very weak. Spacecraft was very, very small. Thruster was very, very weak. Solar panels were not very powerful, but they did mean an acceleration of 0.5 meter per second squared, right? So every second, this thing would move 0.5 meter per second faster. Starts off very slow. But if you're in space and nothing is slowing you down, and obviously you might be like, oh, well, you might encounter some debris. Yeah, that's incredibly rare. Like on the scale of space, encountering an obstacle, whether it be a planet, a star, an asteroid, just someone's crap that got thrown out of the International Space Station, it's so incredibly rare that you actually bump into anything. And yes, I did mean crap literally, but anyway. That ship could just keep going, keep accelerating at 0.5 meter per second every second. Now, after 10 seconds, sure, you're only going 5 meters per second, whatever, no big deal, right? But after 100 seconds, you're going 50 meters every second. After 10 years, you are going close to the speed of light. So this ship, I think, got to a relativistic speed. I don't remember exactly what it was. It might have been like 0.1 or 0.2 times the speed of light. But this is a physical obstacle, moving it at relativistic speeds. So this is real possible physics that needs to be considered for applicable purposes in space travel, mostly. Doesn't really happen on Earth, unless you're studying particle physics, which is what we're going into next, which is where most of this is applicable. Cool? Crazy. Yeah, all right, sweet. Let's do another example. Not a muon, a pion, another elementary particle, one we'll learn about in the standard model. Again, very rare. Generally, their lifetime is at rest, 3.5 by 10 to the negative 8 seconds. So I think that's less than the muon, which was 2.2 by 10 to the negative 6 micro, or is that still negative 8? I don't remember. Anyway, it's an amount. It might actually be slightly more than Muon. Fill out your variables. Everyone in your books, you tell me what t is. Do we know it or not? Put a question mark if not. Tell me what t0 is. Tell me what v is. Hopefully by now you know what c is. Do this on your own. Do this without me. If we manage to freeze it in place, it's 3.5. It's something different. All right. Hands up if you think this number here is relative time. Hands up if you think that's relative time. So the rest of you, hands up if you confidently think it's proper time. Okay. Ask yourself this question. At this time, its mean lifetime at rest, can we measure that time while staying in the frame of reference with the particle when it appears and decays? This time, can it be measured with one clock in the frame of reference with the particle when it appears and disappears? Yes. So it is proper time. Now, hands up if did you finish the calculations doing it backwards? So what was your answer for the proper time? Right, so you measured a faster measurement. Now what you've measured there is what, how much time would pass for the observer according to the particle. So the particle would experience, 1 second or whatever, or that amount of time, and they would see the observer experience more time. But we are looking for the flipped arrangement. So our proper time is, in this case, 3.5 by 10 to the power of 8 seconds. And our velocity is 0.669 c. Let's find t. We want 1 minus v squared is 0.669. I'm skipping steps. I'm going straight to that. The c squared and the v squared cancel. That's it. That's all I need. Let me tidy that up. That was messy. Because you could be given a velocity that isn't a fraction of v, a fraction of c. You could just be given 2.4 by 10 to the power of 8 as your velocity. And then you don't have a c squared to cancel, and it's a bit messier. But you can still do it. Okay, so that equals 1 over the square root of 0.321. Oh, squared. Oh, so T0. Yeah, sorry. Let me sub T0 in on that second line. Too many ones in this, huh? That's a -8, isn't it? As well. -8, -8. That makes more sense, and that does need to be squared. So then we end up with the square root of 1 minus 0.669 squared. God, it's a good thing you guys are around, hey? At least someone here is paying attention. I'm surely not. All right, 1 minus 0.447561. What was it? 0.44, what? 0.669 squared gives us 0.1 minus 0.447561. As many decimals as you can until you come to your actual answer. We're going to be dealing with pretty ugly numbers in this, so... Right. And the square root of that is 3.5 times 10 to the negative 8 divided by 0.74. So 7.43. All right, what did we get? (4.7 by 10 to the negative 8? It's probably 2 because of our P0. Oh, it does specify 3 sig figs. Okay, what is it, 3 sig figs? 4.71. 4.71 by 10 to the negative 8. Yes, of course. I'm not testing you on your math. Yeah, chuck it into the calculator. Just be careful of your order of operations and stuff. Lots can go wrong with this sort of arrangement of calculations. Cool, so what do we know from that? What's the conclusion there? What takes 4.71 by 10 to the negative 8 seconds? According to who? According to us, stationary with respect to the lab, this moving particle takes longer to decay than when we see it at rest and watch it decay. Now for the particle, does it know it's going slower? Does it know it's alive for longer? No. Is it alive for longer? No? No? Not at all. We just see it live for longer. Yeah. That's it. And how can it then travel whatever distance it travels and we see it travel that distance? Because for it, time is the same, but length is contracted. That's what we're going to do next lesson. We've got 5 minutes, so get your notes in check. We'll have time next lesson to do the check your learning for this and consolidate the chapter. I'm going to give you time in class to consolidate the chapter because I'm not going to give you homework while your drafts are still out and about and you're thinking about that. Again, your feedback will hopefully come back this weekend. Wednesday, week 5.